Hello everyone, this is Dilleswara Rao. Last few classes we are discussing on automatic control of aircraft lectures. On that way we are discussing about control system augmentation. So last class we have discussed on control system augmentation related to pitch rate CAS system and lateral CAS systems also we have discussed on last few lectures. So if you refer that last two videos, you can find out that how that control system augmentation is being installed for the pitch rate acceleration and the acceleration feedback systems also, and for a lateral system, how that rudder and roll rate feedback systems also been installed with this CAS systems also we have explained on that. So now we will go to the significance of control augmentation system. Significance means it's we are explaining that CAS system installation with different, new control systems like actually even previously if you find out that one video we have derived delivered significance of SAS system. So there we discussed on that pitch rate and acceleration acceleration examples for that control surface operation, how that SAS system has been installed for that. So now like SAS system, this CAS system also, how it has been installed for control systems and how it has been taken forward for that also we will explain with two practical examples. So let's go into the topic. So first one will be that pitch rate acceleration pitch rate CAS system design, and another one will be normal acceleration CAS design system. So if you see here, these things we have already these things are already we have discussed with previous lecture, and significance of SAS systems also we have discussed the same practical design only. But here, what was the if you find out the difference between what is the difference between SAS system and CAS system, if you see, SAS system is for making that in general words we can say making that aircraft to stable condition. Like if it is going to the unstable condition, that SAS system will help that aircraft to come into that making it to bring back to that controlled stabilized condition. So likewise here also that CAS system, this is also same as SAS system only, but this is inbuilt with the control system operation only. That means there is an addition with the SAS system. The CAS system also been installed there only. So about that also we already discussed on last video. If you refer that, you can have an idea on that. So here we are going to explain with that example like pitch rate CAS system design. So if you see that how this CAS system is being designed for general augmentation, general application, if you see, so there will be a summing amplifier. After that, that transfer function will be this, and then there will be a aircraft control system will be there. From there, that output system will be there. From that output, there will be in between that pitch rate feedback system, that gain feedback system and pitch rate feedback system will be again summing up here. So after that also there will be another forward loop also will be given to here. So this type of system we have been already came into across, like when we have explained that previously also. So we are taking that we are taking that back to here. If you see that F-16 model, for that F-16 model, that the table of contents, if you see here, So here that table of contents are given here, no, that trimmed flight conditions for F-16. So see here, we got an different values for that VT, that means take a, velocity, and angle of attack alpha, and beta will be roll angle, and phi will be the yawing angle, and theta will be that elevator angle, and pitch rate P, and Q will be the rudder deflection, and R will be the Q will be the aileron deflection, R will be the rudder deflection, and throttle, elevator angle of attack, and aileron angle of attack, and rudder angle of attack also. We have been given, one data sheet is been, data sheet has been prepared for that. That data sheet is giving that the nominal values and x CG position with respect to the x that has been given. If you see that x CG, and that phi, that is the angle with respect to the yawing, and that small phi, the theta also been related to that elevator angle also. Different values have been given. These are values how we got from the control system outputs only. For different inputs, what are the outputs we have got it from that control surface, control system transfer function. So here the table will be used. This has been using here that ABC coefficient matrix. If you see from the derivation of from the derivation of that lateral longitudinal equations. So we will get this three coefficient matrix from the solution of the lateral Laplace transform equation. You got A matrix is this one, and the B matrix, and the C matrix. So here that A, B, C matrix are giving the values for that alpha, Q. Alpha is the angle of attack, Q is the pitch rate, and VT will be the velocity, and theta will be the elevator deflection angle. So for that, what are the values? These are the output values we need to get it, because when a control surface has been operated, means these outputs will be fed into that control surface, and these outputs where we will get from the inputs of that inputs of that total system. So the system is like looks like this only. So here you see the elevator actuator and alpha filter dynamics. The sign change will be incorporated with actuator output only, because if you remember the sign changes for elevator and aileron. So for a positive side, what will be the sign change, and negative side, what will be the sign change, and the negative pitching moment and positive pitching moment, and negative rolling moment and positive rolling moment. These things already we have seen. So like that, here the values we will take it from according to that sign changes only, because why these sign changes are required, because every time we cannot every time we cannot judge that that aircraft has been going this way or this way. So that way of turning also depending upon how much turn it has been taken from that previous controlling inputs only. So the design procedure will be looks like a alpha loop, and intersect expect that actuator to pitch rate transfer function to choose the position for PI. PI is the particular integrator value that will be the 0, and likely that yields to that satisfactory root locus plot. If you see that root locus plot for a given function, so previously that root locus plot we did it with conventional calculation only, but now we are giving one MATLAB program here. If you see that MATLAB program, this is for making that plot only. So here that the values in the transfer function, if you remember the transfer function, suppose the transfer function is like that. So for these transfer function, what will be the frequency response also, we will get it from this MATLAB program also. See here the coefficients like AP, BP, CP, DP given here, and that system P and system A, and that system responses for that logic have been given like series CCA and CSP, and that ABC will ABCD will contain this one, and that acceleration will ACL will be how we will get A minus B star K alpha into K alpha 0 into C, so that ZPK will be the corresponding values from that one. So if for each and everything we have given here, AP means x1, that is alpha, and x2 will be q, and this is BP will be the elevator input, and CP will be that alpha x1 y1 being given. So Z component is not there, and this is the plant thing we have given, and the CCA will be the actual actuator sign changes. I mean how sign changes will be, and that alpha filter and actuator plant plus filter loop also been given here, and extracting the values from there, and after that closing that alpha loop. Like after getting that one, we will close that loop. Like while closing the loop means what? We are giving for different values, that loop will be operated up to here. After that, it will be it will again start from the previous one. So the procedure will be given by that MATLAB code that has been given. So the filter has been defined into two inputs and two outputs. So see here two inputs and two two outputs also we are getting out from here. So the loop feedback gain, the K alpha is chosen for the 0 poles, and the gain of Q by W U1 transfer function will be calculated from this from this Laplace transform equation. How that transfer function we will get it, see here. So this is the Q by U1 transfer function for that given pitch rate CAA system. So that means that if you see here, that the transfer function has been the transfer function it is showing now. So this transfer function will be Q by U1. So that based on this transfer function only, that integrator will works. Okay. So the final design will be relatively, unless that integrator plan can be moved well with left or right, left or made coincide with 0 also. Like when that if you see that root locus plot, if it will go to that left side, that means above, away from the imaginary axis, or it will go to 0. If it is going to 0 means that going near to that imaginary axis. So some trial designs that have been shown the demands of a smaller amount of alpha feedback than that is been used in previous pitch rate essays. Then it will be demonstrated by comparing with two different values of K alpha. So that SCS values, that here the K alpha means what? Pitch rate values only. So the entire function that has been depended upon for given pitch rate value, that is K alpha. Here we have taken that 0.02 only. So the behavior of outer loop with outer loop on the root locus will be added with the PIE compensator, and can now be anticipated as a KP. That is here that alpha rate, and this is pitch rate KP. The integrator pole will be moved towards the 0 at when it is KP value is minus 1.029, it is going near to that 0, and the compensator 0 should be left of this 0 only, that compensator left of this 0, and the short period poles will circle around the compensator 0. So for that, the following commands have been used for PI integrator. That is the command, the MATLAB command we will use for this alpha loop has been given here. If you see that one, that series SI and S3 is there now. So this will gives you that plot. I mean the plot for here the plot what we got, we will we required our locus. Our locus will be that AA, BB. These are all the components we have already defined previously. Based on that components, that plot have been given here. So that root locus plot have been given in for figure 1. So if you see that figure 1 root locus plot for pitch CAS, so here you see that root locus plot has been going towards the 0, and it has been somewhat increasing, like increasing here, and then it is going to there, and that alpha loop also been given here. So here the value of k will be 0.9 for this thing. So if you see that when s equal to 0, s equal to -3, then the Kp reaches about 0.5. So see here, when s equal to minus 3, then it will be reaches to Kp reaches to minus 0.5, and Kp equal to 0.5, and the filter and the actuator poles from a second command pair of that integrator pole has been moved to s equal to minus 0.91, and the short period pole set s will be equal to 3.2 into 3.2 into plus or minus j34. That means for s equal to 0.9, if the roots of s is minus 0.9, then another root is coming as a complex number only, that is minus 3.2 plus or minus j3.4. So that means increasing Kp causes a second complex pair to quickly become less damped. That means when that Kp value, here from 0.5 to 0.9, if it is going, then that that is getting less damped only. So while the integrator pole moves only slightly faster left, that integrator move, you see that it is showing like this now. So that means that integrator plot is moving slightly near to that 0 only. So if the amount of if the amount of alpha feedback is reduced, the integrator pole will be moved closer to the 0 at s equal to minus 1.029 before the second complex pole pair has been appears. So while maintaining that satisfactory short period pair, the things will be more stable at this value at minus 1.029. So the alpha feedback was generally will take the value of k 0.08, that is k alpha, and the compensator 0 was retained as 0 s equal to minus 3. Then with the intention of causing that short period poles to pass near the near s equal to the near s equal to minus 4 plus or minus j 3. If you see here, here that short period pole and Fugite mode approximation values are we are getting it 5 and 0.8. So here for s equal to minus 3, when k alpha equal to 0.08, so you have the values for s we are getting it minus 3, and another value is the complex number only, that is we are getting minus 4 plus or minus j3. So the root locus plot was the same shape that has been shown in figure 1 with the Kp equal to 0.5 also. So the slow integrator pole reached to minus s equal to minus 1.9, and the stopped moving left to that short period poles reached at s equal to 0 plus minus 3.4 into j3. So the actuator and filter poles are still short of combining to form a complex pair. So that closed loop for transfer function for these things will be like what? That pitch to roll rate will be q by r equal to 101 into s plus 3 into S plus 10 into S plus 1.029 by S plus 10.7 into S plus 13.7 into S plus 1.02 into S plus 3.43 plus or minus J 3.03. So these things we again, if you remember that time, how this transfer function we have set this for this control surface is from the previous from the solution of that differential equation only. So this will be considered for designing of closed loop step response that will be simulated with following code. So if you see that step response, we will get it from this code. So that acceleration and system code and the step response will get it from this one. So those things that step response plot, if you see that step response plot for non-zero and with the compensator 0, that the k value, when the k value is changing from non-zero value with the compensator 0 thing, how this response amplitude for with respect to time has been given here. So the figure this one this is a figure 2 only. So this will show the step response. So this step response for first so this is the first time and large overshoot about 20% overshoot. If you see here, there will be some increase of 20% and does not satisfy the deadbeat requirement. So the other curve shows the pitch rate step response when the compensator 0 is moved. So compensator 0 is being removed. So the rise time is now longer, but the settling time is about about the same, and the overshoot time is only around 2% only. So this is the potentially, it will be the good design for moving up with same feedback gain to complete the longitudinal dynamics. So with feedback gains, K alpha with 0.08 and Kp will be 0.5 will be used for full dynamics in about the example also that has been shown here. So the again that transfer function we are using here, this one is the q by r has been given here. No? So this transfer function will subset, gives you the subsets of folds and zeros given by short period approximation, and the Fugite mode was degenerated to real pole with this small amount of alpha feedback. Also the Fugite poles are cancelled. So would pay no part in the pitch rate response in this case. So this example, these things will gives you the pitch rate. The design of pitch rate only. So the actual design will be optimized by careful compensation with flying qualities requirements, pilot requirements, and flight test only. So during that design process, that design must be performed at several points, because here for every transfer function there will be a lot of routes have been coming out for this one. So that routes have been every time it will be tested and it will be presented for the testing response of that control surface. So that when the speed altitude develop envelope, if you see that feedback gains will be function of some scheduling parameters such as dynamic pressure, and that means if you see that scheduling parameters, previously if you see that CAS system that has been when the control surface design is been given, so that time that is totally depend upon that is totally depend upon how that dynamic, because when we are attaining a big values, a big when pitching rate is more, so that when it is landing or when it is getting take off, that rate values will be more. So that time the values will be getting high. So that there will be that dynamic pressure will be a compensator thing will dynamic pressure will be a big compensator for giving these values also. So another example will be that normal acceleration CAS design. So that if you see that normal acceleration, previously that pitch rate CS system, and another example will be that normal acceleration system. So again for the normal acceleration also, if you see that summing amplifier and that integrated function will be there, and that pitch rate thing will be there, and after that that aircraft control surface thing also been installed here. So the configuration shown in figure 3 will be the configuration shown in figure 3 will be given like the dynamic the dynamics will be as same as that previous case only. So but the output equation for that normal equation will be determined like it will be shown like the numerical linearization of that above equation with the accelerometer will be about around 15 feet forward that CC, 15 feet forward for CG, and the nominal flight condition as shown in that first table. The output equation will be for that. This is AN will be the normal acceleration only. So that normal acceleration will be 0.003981 and 0.30003981 VT plus 16.29 to alpha, 16.26 to alpha, and that 0.9787 Q minus 0.048 delta E. So here the values have been depend upon that VT, alpha, Q, and that delta E. So here that VT will be the somewhat weakened values. So and VT and theta will be dropped with the final results check will be complete dynamics only. So the MATLAB commands for this for this system, if you see here. So this is the MATLAB command for previous system. If you see again, it is also having the input values and elevator input and that pitch rate and angle of attack values also been given here. So again here the output value will be that the transfer function have been given here, and that loop function have been closed here. Then that AN by U1 transfer function also we have given here. That AN by U1 transfer function, if you see here, so this will be the AN by that acceleration with velocity transfer function is this one. So the effect of inner loop pitch rate feedback is to speed up the two slow poles and at a quite low gain the poles from when the poles gain is very low, when s equal to minus 1.9191, that combines the actuator pole to form a complex pair. So the speeding up these poles is desirable as fast response has been covered. So but as noted previously, the amount of pitch rate feedback is limited by practical consideration. If pitch rate is limited by practical consideration, the value Kp will be equal to 0.4. Pitch rate is 0.4 and that elevator deflection per degree per second will be, and in line with past experience that has been we set it from 0.25 to 0.5, and that leads the transfer function will be that AN by U1 will be equal to it has been changed. It has been given like this. So the outer root locus with added PA compensator will now be anticipated. The compensator pole will be will combine the S equal to minus 0.8601 from complex pair, and these poles will be moved toward the complex zeros of this equation. That behavior we can get it from the position of compensator 0 only. If the compensator 0 is well, and if it is left at S equal to minus 0.8601, the branches will be deflected only slightly to left the landing of that complex zeros only. So at the same time, a pole is equal to 0 or minus 7.661, so that will move the compensator 0. I mean, how that compensator 0 has been moving towards to that towards to that element, that imaginary axis, and how that overshoot has been coming out also we have seen in previous previous example. So the potential slow pole problem, the complex zeros are well damped, and it will be difficult to achieve the fast well damped complex poles together with the real pole. So, here you see the root locus plot for this transfer function with k equal to 3. So, the alternative place for compensator 0 close will be when x equal to minus 0.86. The pole is effectively cancelled. The locus of that short period pole will be break away from the real axis somewhere close to the pole at s equal to minus 7.661. So that the locus of short period pole will be break away from the real axis. That is been when this is the real axis, and this is the imaginary axis. So when it is getting away from the imaginary axis, means it is getting positive values, but more positive values also not advisable here. So that should be in between that design values only. So that the sensitivity of the pole gain variation and noise pickup and possible advantages of additional compensator pole and zero will be considered here. Like here the sensitivity of pole gains, like when that pole gain variations, gain feedback variations are more, and that noise pickup is somewhat reducing. So that will be the advisable things for making up this into, making up this into installing the action. So here the figure, above figure will be the root locus plot for this thing. So the effect of imperfect cancellation is visible at s equal to 0 minus 0.9. If you see, and s equal to minus 0.9, here the real axis values is getting at minus 0.9. So that time the locus of that getting at a short period poles that shows the satisfactory damping and natural frequency will be achieved without an additional local compensator only. So the short period poles will be made well damped, because that the compensator 0 can be anticipated to cause a overshoot in the closed loop step response. So when the root locus calibrated with Kp alpha, Kp and alpha value at a Kp equal to 5, that will be gives you the short period poles at s equal to 3 plus or minus j 2.18. So for here that short period and Fugate mode values will be like 3.7, and the damping ratio will be 0.87 only. So for that acceleration to that roll rate transfer function will be designed like this. So the figure 5, if you see here again, that normal acceleration step response, if you see, so for figure 5 shows the closed loop step response for this above transfer function. The response will be fast and well damped. So the initial rate of rise will be particularly fast because of pitch acceleration component of that response only. So that rate limitations of the elevator actuator would be modify this response slightly. So this associated pitch rate compensate shows an overshoot approximately around 100% only, but the C star response will be fall most exactly to that middle of the things. So the level that C star values were computed from that component Q, and that normal acceleration output will be from the equation of closed loop Jacobian matrix. That Jacobian matrix, if you see, that contains that stability derivative functions. So that from that stability derivative functions only we have got that transfer function. From the transfer function, the roots of S only we are making it for solution of this thing. So that the initial time response was performed so that steady state value of C star will be determined for normalizing the step response. So here the closed loop transfer function obtained by applying that feedback gains will be given like that a n by r will be this one. So the transfer function contains two very good approximation. So that is the poles and the zeros of 4. That means previous equation 4, if you see the poles and the equations of 4, thereby justifying the use of short period approximation. In this equation 5, that phugoid mode is degenerate and one pole is unstable, whereas in pitch rate SAS that stable phugoid was achieved with basic stability augmentation system. So this is because normal acceleration in Q1 that contains value of Vt, and it is been compensated being feedback in a positive sense. So the phugoid mode is almost cancelled by transfer function 0 in this case, and the unstable pole is very slow. The unstable pole is probably immaterial in this flight control thing only. So to avoid the inner loop alpha feedback and using a gain in acceleration loop, an alternative possible to modify this feedback gain for this normal acceleration will be we have been used it from that previous equation. If you see it in see this equation in designing of SAS system, so that time we have given this equation that an will be equal to that normal force plus GD and ED cos theta and cos phi. So if you remember this equation, this equation we have used in that SAS system. That SAS system design only. So here the theta component will be the correct sense in stabilizing that phugoid mode. So that the control system will be steady climb with dive in with no control stick deflection. Also it will be getting a more value, more controlling for making it that normal acceleration. So this way that CA system like control augmentation system will be perfectly that has been installed in this normal acceleration system and pitch rate system with this non-zero component and this zero component C star values also. If you use these values, how this system will be well advanced, and how that system will be well posed for designing that into normal normal stability things also. How we can get it from this thing, get it from this equations also we have shown here. So this is all about that CS system only. So how this CS system has been designed and how it has been applied for different feedback systems also, and how it can be practically we can explain with practically we can explain with that application with pitch rate system and roll rate system also there, and other examples with lateral direction also will be there. That has been available in this textbook. If you see that Stephen BL textbook, so if you want to have a further reference for your consideration, you can refer that textbook. So this is all about the significance of control system augmentation. So next class we will see it on the autopilot system and gain feedback system design also we will see. So that's all about this one. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.